Welcome, guys. Today we're going to discuss the final topic in the chapter of operator theory, and that is the closed operator. And we start with the definition. So, in this section, we will discuss linear operators which are defined on a subspace of a norm space. So, we write this T from dt, which is a subspace of x, to y, and dt is usually a dense subspace of x, and t is not continuous, because if t is continuous, then we can just extend t by continuity of x. Now let x and y be norm spaces. A mapping t from dt, which is a subspace of x, to y is closed if the following statements hold. And what is the following statement? The statement is, if xn is a sequence in dt, is a convergent sequence with limit x, so it means that limit n tending to infinity xn is equals to x, and it is a convergent sequence in dt, so this belongs in dt, and txn converges to y. So let me write txn converges to y, so or I can write it as limit n tending to infinity txn. So limit, so this is one word, limit txn is equals to y. Now this implies that tx is equals to y. So let xn be a convergent sequence with limit x, and let txn converge to y, then tx equals to y. This, when this holds, then I can say that my operator t is closed. Now this does not imply that d of t is closed. That is, it is not saying that if you take any sequence in xn in dt, it will converge to x. It is saying that if xn is convergent sequence with limit x, it does not mean that every sequence would have a limit which converges in dt. The next thing it is not saying is that t is continuous, means that xn converges to x, so txn converges to tx. This is not what the theorem says. So dt is, so this does not imply that dt is closed or t is continuous. Now I make a remark that all continuous operators are closed, because continuous means that txn converges to tx, so thus tx equals to y. So we can get closedness from the definition of continuity. And now I have two examples. The first example says that I have my domain defined on C01 with the subnorm, and dt from dt, which is f to f dash, with dt as being a subset of C01, that is C101. The mapping is closed but not continuous. So now we see that this is our function, and this function belongs to C101, and the sup norm gives me 1, and when I do the derivative of that, I get the supremum norm as n in 01. Now I say that the supremum norm of this is equals to un dash, which is equals to infinity, so that is t is unbounded, so this mapping is closed but not continuous. And in the second example, I say that let fn be a sequence with the property that fn and tfn are convergent. So if you have a sequence of differentiable functions on compact intervals, that is closed and bounded intervals, and fn's themselves converge uniformly to f, so fn converge uniformly to f, and gn converge uniformly to g. Now it's saying that okay, fn and tfn are convergent, denoted by their limits by f and g, so that fn and fn dash converge uniformly on 01 to respectively f and g. Now it follows from the theorem from analysis 1 that f is differentiable with f dash equals to g. This is the statement that f belongs to C101 with tf equals to g. So it is just essentially saying that exactly this statement, that Fn converge uniformly to F, Gn converge uniformly to G. So I'm just saying that we have a theorem analysis one that we know that okay, F is differentiable and F dash is equals to G. Now we do the definition of graph of a linear mapping. So I define graph of a linear mapping T from dt, which is a subset of x to y, is the subspace. So this is the subspace G of T, and it is a closed subspace of x hot cross bun y. Now the next proposition is okay, let x and y be norm spaces. The linear mapping T is closed if and only if GT is a closed subspace of x hot cross bun y. Now GT is closed. When I say GT is closed, I mean GT is closed as a subspace of x hot cross bun y. So let x and y and be a convergent sequence in GT, and it converges to x comma y. Then x comma y belongs to GT. And one more thing that I want to write about GT is that if x comma y belong to GT, if and only if y is equals to tx. So this is the thing I want to write about GT. Now the theorem says, or the proposition says, that suppose xn converges to x and txn converges to y, and T is closed if and only if y is equals to tx. So this is the definition of saying that okay, T is closed as an operator. Now closed. Now I say that xn and txn converges to xy, okay, and GT is closed. And it is the same if and only if condition that y is equals to tx. So what happened here? So I say that T is closed as an operator. By the way, this is an if and only if. So T is closed as an operator if xn converges to x and txn converges to y, and T is closed. And this is a if and only if y equals to tx. So this is the definition of T being closed, that xn is converges to x, txn is converging to y, then y equals to tx if T is closed, if and only if. But that's the same as saying that I have a sequence xn, txn, it converges to xy, and this xy lies in GT, and if GT is closed, then this xy will lie in GT, but xy belongs to GT means if and only if y is equals to tx. So it's just the same thing written in two different ways, you know, so we can make the transition from anywhere to anywhere. So I hope this is clear. And now we do another proposition. We say that dt is a Banach space with respect to the graph norm. Now this is the graph norm, and I say that it is a Banach space. So let xn be a Cauchy sequence in dt. And now when I say that this xn be a Cauchy sequence in dt, I mean this is xn comma txn. Now this is precisely the statement that xn txn is a Cauchy sequence in gt, because yeah, this is exactly the same statement, because my space dt is equipped with the triple norm, and any element here can be represented only as, you know, the norm of any element can only be computed in this way. So these two statements are equivalent. Now since gt is a closed subspace of Banach space x hot cross bun y, it is itself a Banach space. That we know, that closed subspace of Banach space is a Banach space. Now it follows that xn txn converges to xtx in gt, and this is precisely the statement that xn converges to x in dt. So the main thing that happened here is, okay, I showed that gt is a closed subspace of Banach space x hot cross bun y, and closed subspaces of Banach spaces are themselves Banach spaces. So I can say that dt is a Banach space with respect to the graph norm, because dt is a subspace with respect to the graph norm precisely means that there is a sequence xn txn in gt and it converges the limit to x dx, and that limit lies in gt. Therefore I can say that dt is a Banach space with respect to the graph norm. And now t from dt, this space to y, is continuous. Now why is it continuous? Now this assertion follows from the inequality. So if I see that norm of tx is less than equals to norm of x plus norm of tx, which is less than equals to triple norm of x. So I have, so let's see, so it is going from dt, which is a cubed with the triple norm, to y, this t. So if I have any element here which can be represented as, say, x, so what I needed to prove anything that continuous was I always used to say that tx is less than equals to m times norm of x. But norm of tx remains the same, and this should be in the space dt, and this is in the space y. But in the space dt, the norm is defined as, so let me write the above equation again. So I can write that norm of tx in y space is less than equal to m times the norm in x space is again this. So this is what I want to prove, so this is to prove. So I can write definitely that tx is less than equal to, so let me write, I can write txn is less than equals to norm of x plus norm of tx. Well, of course, but this is less than equal to norm of x, so I can say that this transformation is continuous, because continuity just meant that, okay, norm of tx should have been norm of y in space dt, and as norm of tx in space y should be less than norm of triple norm of x in space dt. So I can say that, make two assertions very clear, that dt is a Banach space with respect to the graph norm. Okay, now if xn is a Cauchy sequence in dt, this is precisely the statement that xn txn is a Cauchy sequence in gt. Now since gt is closed subspace of the Banach space, it turned out that it itself is a Banach space, and therefore I can say that xn txn converges to x dx in gt, and this is precisely the statement that xn converges to x in dt. So it is a bit mind bending, a bit mind melting, but that's life. So the closed graph theorem says that, well, before I discuss the closed graph theorem, I would discuss this corollary with you. So let x and x equipped with one norm and x equipped with two norm be Banach spaces, and suppose there is a constant c that that norm of x1 is less than c times norm of x2. So this is like the norms in two different spaces. Now it follows that these two norms are equivalent. So I am saying that basically on Banach spaces all norms are equivalent. So this is the first thing that I want to remind you of before starting the closed graph theorem, that on Banach spaces all norms are equivalent. Now essentially what the closed graph theorem says is, so now let's look at the closed graph theorem. So I have two Banach spaces x and y, and I say that t from x to y is a closed linear mapping. Now it follows that t is continuous. So what happened is, now x equipped with two norm and x equipped with this three norm are Banach spaces, and I know that in Banach spaces all norms are equivalent. So according to the corollary of open mapping theorem, these are equivalent norm on x. Now if they are equivalent norm on x, and I knew that x from triple norm to y is continuous, therefore x from 2 norm to y is also continuous, because if you have norms as equivalent, if you establish the equivalency of norms, then all topological properties would be the same, all open sets would be the same. So the only idea that I want you to remember is, if the norms are equivalent, then operators which are continuous to this norm would be also continuous with respect to this norm. That is exactly what I want to say, and that is all I want to say. So that the closed graph theorem essentially says that I prove the equivalency of norm. First I take the norm of dt, and then I say that dt equals to x. So I already knew that. Now let me put it like this. So I already knew that dt equipped with the triple norm was a Banach space. Now I put dt is equals to x equipped with this triple norm, and I proved that okay, this is also a Banach space. Now t was continuous. I proved above that t was continuous. So t from dt equipped with triple norm to y was continuous. Now if I extend dt to x, then this is also continuous. So this to y, this t is continuous. And now I proved that these two norms, the triple norm and so this norm and this norm, are equivalent. So t, if t was continuous with respect to this norm, then t is also continuous with respect to this norm, and that is all I want to say. So then now finally I would like to talk about the theorem. So again, x and y are Banach spaces, and t from dt be a closed linear bijection. Now it follows that t inverse from y to x is continuous. So let me see, closed and linear. Now when I see Banach spaces and I see closed and linear, I know that it is continuous. What is continuous? T from dt to y is continuous, because this is exactly what the closed graph theorem told me. It told me that that x and y be Banach spaces, t from x to y is a closed linear mapping. So t from dt to y is a closed linear, and this is also bijection, by the way. Now first of all, I can say that this t is continuous. So t from dt to y is continuous. This is the result of closed graph theorem. And the inverse function theorem tells me that if I have a continuous, surjective and linear mapping from x to y, then the inverse is also continuous. So that's what the inverse function theorem told me. So I know that this inverse from y to dt is also continuous as a result of inverse function theorem. But now on the other hand, the inequality if you look at this inequality, it shows that the identity mapping, so identity mapping is going from dt to x. So this is the space it is going to, so I goes from this to this. So I can say that of course norm of x is less than equal to norm of x plus norm of ix, and thus the identity mapping is continuous. But now you see that t inverse from y to x can be written that though this identity mapping goes from dt to x, it is pretty continuous because of this inequality. And after that there is another continuous mapping, t inverse, which goes from y to dt. So I can say thus that t inverse from y to x is also a continuous operator. And finally, in the final example, I show that I have a function in C01, let f be an element in C01, and I show that this differential equation u dash equals to f with the boundary has a unique solution in C01 which depends continuously on f with respect to the supremum norm. So now if you finally look, now this t is from C01 to C01. Now if I just need to compare it's just the application of the theorem above. So if you see that, okay, there are two Banach spaces and t from dt to x be a closed linear bijection. So I can see, okay, let x defined like this, y is defined like this, and dt is defined like this. Now observe that t is closed and t from dt to x is bijective with inverse given like this. So what did I had before? So closed linear bijection means that t inverse from y to x is continuous. So therefore t inverse from C01, so t's inverse would go from again T inverse would go from again C01 to C01. So this T was closed, linear, and it was a bijection. And so x and y were one-arc spaces. T from dt to y be closed linear bijection. Now it follows that y inverse, T inverse from y to x is continuous, and this is exactly what happened. So observe that T was closed and it was bijective, and it was closed, linear, and bijective. So therefore T inverse would be continuous, and therefore I can say that if T inverse is continuous, then T inverse of f would be u, and I can say that okay, well, so T of u would be, say, u dash. So if T inverse is continuous, then T inverse u dash. So if T inverse is continuous, which means that T inverse of u dash is equals to T inverse of f is equals to u. Now it follows that the equation Tu equals to f has a unique solution which depends continuously on f with respect to the supremum norm. Okay, so as soon as I establish that this T inverse is continuous, I can say that this equation Tu equals to f has a unique solution which depends continuously on f. So the solution to this equation depends on f with respect to supremum norm.